Okay, good evening, Moffat. This is the end of everything. Following the talk I gave you earlier in the year about the beginning of everything, this is the bookend. And as you can see from the subtitle, I'm talking about the fate of the Earth, the Sun, the galaxy, and ultimately the universe. So we're going on a journey to eternity and beyond. I'll be telling you a little bit of background first before talking about the future of the Earth and the Sun and the solar system, the far future and the fate of the stars and the galaxies, and ultimately the far, far, far future and the ultimate fate of the universe. But to avoid leaving you on too depressing a note, I'll finish with a slightly more upbeat epilogue. Okay, so a while ago I told you about the beginning of everything, how the fact that we know that the universe is expanding, and so we deduce that in the past it was a lot smaller, and everything that is currently in the observable universe, a sphere of diameter about 100 billion light years or so, everything used to be a lot closer, separated by just centimeters. Is it possible for you to mute your microphone, please? So everything was a lot closer together. Everything in the observable universe was separated just by centimeters. And as the universe expanded, it cooled and started to create the matter, the neutrons, the protons that ultimately became the hydrogen and helium that we see in the universe today. So in this talk, I'm going to be following a timeline, and I'm going to be using these numbers across the top of the screen to indicate where we are. Each box represents 10 times into the future, 10 times further into the future. So we're going to be talking about 10 to the power 3, 1,000 years into the future, 4, 5, 6, 10 to the 6, a million years, and so on. 10 to the 9, a billion years, 10 to the 12, a trillion. So we'll be using these red boxes in the top just to keep an eye on where we are as time goes by. Otherwise, it's very easy to lose track. And I'm grateful to the work of Adams and Laughlin, who produced a paper 25 years ago that laid out the likely timescales on which various astrophysical phenomena are likely to happen. And I've used their paper to get my slides in the right order. So I'm jumping around between topics. I'm not just covering the Earth and then the Sun and then the galaxy. I'm jumping around trying to keep to a time order. And rather than start just a few years into the future, I'm going to jump to 10 to the power 4 years, 10,000 years into the future. Let's assume we don't blow ourselves up. Let's assume we get climate change under control. We know that certain things are going to happen. For instance, in 10 to the 4 years, because of the precession of the Earth's axis, as indicated by this cartoon on the left, we know that the Earth's axis is pointing to a bit of sky that basically circles every 26,000 years. There's this 26,000 year cycle, which we call precession of the Earth's axis. That means the direction that the Earth's axis is pointing is mapping out a circle on the sky. So at the moment, the Earth's axis is pointing close to the North Pole, which we call Polaris. And in another 10,000 years or so, it's going to be pointing in the other direction towards what will be the new pole star, Vega. That will make it easier for Boy Scouts to know exactly which way is north. But it does have one consequence. If we think about it at the moment, because of the Earth pointing at Polaris, we are nearer to the Sun in January during northern winter, when the Earth's axis is pointing away from the Sun. But when the Earth's axis is pointing in the other direction, we're going to be nearer the Sun during northern summer. And that's going to exaggerate the seasons, because we'll be closest to the Sun, receiving more radiation, at the same time that we're tilted towards the Sun. And these variations in the Earth's climate, due to changes either in the Earth's spin or the Earth's orbit around the Sun, are collectively called Milankovitch cycles, and I'll mention those again shortly. In 10 to the 5 years into the future, the Voyager spacecraft are going to be passing nearby stars. Remember, the Voyagers were launched in the late 1970s, going past Jupiter, then Saturn, and in the case of Voyager 2, also Uranus and Neptune, and both are leaving the solar system. They're heading off in different directions. At the top left there, Voyager 1 is heading off in the direction of the star Gliese 445. And at the bottom of the diagram, Voyager 2 is heading off in a different direction towards the star system Ross 248. And it's going to take somewhere between 10 and 100,000 years for those Voyagers to reach those star systems. Given that it's unlikely they'll be stopped by any civilizations in those star systems, what will probably happen is that those Voyagers will enter the star systems and then leave them at a similar velocity to their entrance velocity. And they will go on and pass through probably hundreds, if not thousands, of solar systems for the rest of their life. Pioneer 10 and 11, also on this diagram, were launched a little bit earlier, but they're travelling more slowly. Pioneer 10 on the right there is heading off in the direction of Aldebaran. Pioneer 11 on the left is heading off in the direction of the centre of the galaxy. We know that there have been repeating cycles of glacial and interglacial periods, so-called ice ages, and these tend to come and go according to the historical records every 100,000 years or so. And we believe that Earth entered a warm phase, an interglacial period, not that long ago, and so we would predict that the next ice age is predicted on a timescale of order 100,000 years. This is another manifestation of Milankovitch cycles due to changes in the Earth's orbit. On this same timescale of order 100,000 years or so, we know the Earth is going to continue to slow down. In a separate short talk, I describe how it is that the Moon is acting as a brake, if you like, on the rotation of the Earth. And after this length of time, the Earth would have slowed down to the point where leap seconds, extra seconds that need to be inserted into our clocks to keep the rotation of the Earth synchronized with our clocks, instead of adding one every few years, which is the current situation, we would need to add a leap second every day. In other words, the length of the day would be approximately 24 hours and a second, not 24 hours as it's currently defined. We know that stars are going to go supernova. We can't predict exactly when, but it's thought that on this sort of timescale, 100,000 years into the future, there will be the possibility of a number of supernova. For instance, Eta Carinae is a very massive star in the southern hemisphere, and this particular astronomy picture of the day shows a Hubble Space Telescope image showing that it's rather unstable. It's already been blowing off the outer atmosphere of the star, producing this planetary nebula, and it's likely that this is a candidate to go supernova in the not so distant future. But of course we can't predict exactly when. It could be beaten by other big stars like Antares or Betelgeuse. Here's an image of the sky over Prague Observatory. And here, the person taking the image has produced an image of Orion. Perhaps you can see Orion there, and Taurus and Gemini, etc., Sirius down here. But here, the person who took the picture has made Betelgeuse as bright as it might appear when it goes supernova. So it'll ruin the constellation of Orion, but it'll be a rather spectacular sight, both in the night sky, possibly even in the day sky as well. But it's not just supernova we have to worry about. On a timescale of 100,000 years, the star Wolf-Rayet 104 might die. And even though it's 7,000 light years away, rather more distant than, for instance, the few hundred light years of Betelgeuse, even though it's at a greater distance, its death may result in more of a problem for us than even a nearby supernova. And that's because this is a very rapidly rotating system, and we don't fully understand the mechanism, but rapidly rotating systems often produce jets. And when this star dies, if the jet happens to be pointing in the direction of Earth, then we could receive a significant dose of gamma rays from the death of this star. And that would indeed be a problem, even at that distance. But we're hoping that the alignment of the jet is not exact enough to cause us too much of a problem. A million years into the future, various things are going to happen. We are orbiting around the centre of the Milky Way, as are all the other stars in the Milky Way. We're all on essentially independent orbits, but as we go around the centre of the Milky Way, every once in a while, we'll get close to some of our neighbours. And on a timescale of 1 million years, it's been predicted that the star Gliese 710 will actually pass quite close by. This has been determined by accurate fixes on all the nearby stars their positions and their velocities given by probes such as Gaia, for instance. Notice that Gliese 710 is actually going to come quite close to our Sun. It's going to be closer to our Sun than most of the objects in the Oort cloud, a large sphere of lots of icy bodies. And as it does so, it's almost certain going to be disruptive to all of the objects, or at least a large number of objects in the Oort cloud. So it will probably nudge a lot of objects and give them a tidal pull, which will send them raining down into the inner solar system. So it's been calculated that there will probably be naked-eyed comets probably every few weeks for 1 million years because of this nearby star nudging all of the objects in the Oort cloud. Note that for a little while, our solar system will actually have 2 suns in it, just like other systems that we know about. Still on 1 million years, meteor crater Arizona. Does that mean we're expecting something like this impact every 1 million years? Excuse me a second. No, it's not an impact like this every 1 million years. It's reminding us that in 1 million years, a lot of impacts will disappear. We look at this impact and we think to ourselves, wow, what a stroke of luck. It just missed the visitors centre there. I mean, very close call, that one. But in 1 million years, we wouldn't expect to see that many craters simply because they get weathered on the Earth. Wind and rain would mean that any impact craters more than 1 million years old will simply be invisible. That's why we don't see that many of them on the surface of the Earth compared to, for instance, the surface of the Moon. But don't believe that things on the surface of the Moon will last forever. Even the footprints of the Apollo astronauts won't last forever. There's no weathering in the same sense as on Earth, but the Moon's surface is bombarded with micrometeorites. It is being pulverized, and the regolith, the surface of the Moon, is continually being disturbed by these micrometeorites that will eventually remove the footprints, and it's been calculated all evidence of the Apollo landings, even the lunar module descent stage, even the lunar rovers, even the surface equipment, will eventually be completely eroded by the micrometeorite impact if you wait long enough. Moving to 10 million years into the future, we can think about what's happening to Pioneer 10. We said it's leaving the solar system and will probably pass another star in 30, 40,000 years or so. So on a timescale of 10 to the 7, it will probably already have passed through perhaps 1,000 solar systems. And if anybody in any of those solar systems pick it up, they will be able to look at the plaque that's on the side there, and they'll be able to see where Pioneer 10 came from. The picture on the left is a pulsar map giving our coordinates, and the picture at the bottom, the little cartoon, indicates that this particular probe came from the third rock from the Sun. But after 10 million years or so, it'll be difficult to read this plaque because Pioneer 10 is moving through the interstellar medium, which isn't strictly speaking a perfect vacuum. The material between the stars might be very tenuous, but if you're travelling very fast and you're travelling for millions of years, eventually the plaque will become pitted with impacts from the debris, the dust that's lying around in the interstellar medium. So if the spacecraft is not picked up in the first 1,000 or so solar systems that it happens to go through, if anybody picks it up after that, they will probably not be able to read the plaque because it will be just too eroded. Moving to 10 to the 8 years into the future, we can think about the fate of Saturn's rings. But before we think of the future, let's just think of the past. How did Saturn's rings get to exist in the first place? Some people think that a moon such as one the size of Mimas might have made Saturn's rings. If you destroy a moon by impacting 2 moons together or have a moon impact with a comet, then it's possible that the debris formed Saturn's rings. And when you look at a moon like this, you might think to yourself,
that's no moon, it's a space station.
Because it does look rather odd with such a huge impact crater there. And simulations have been carried out that indicate if you take a moon about the mass of Mimas and pulverize it, let's just assume a comet hits it or something like that, if the moon is pulverized, what happens to the debris? You might assume that it just goes around Saturn as a little cloud, but actually it gets stretched out in its orbit quite quickly. Notice the timescale in the bottom right. It only takes a matter of days or weeks to form what is recognizable as a ring system. And in the million years that follow after the formation of Saturn's rings, each of the little icy particles will end up drifting down towards the surface of the planet. They're not strictly speaking in circular orbits, they're in spirals because they're all interacting with each other, and they will spiral in towards the surface of Saturn. And this process has been going on for millions of years, and that's why we see the rings the way they are at the moment. The structure within the rings because of the interactions of the individual particles and those particles with Saturn's moons. But if we wind the clock into the future, we can predict that this process will continue and all the ring material will eventually spiral in and rain down on the surface of Saturn. So Saturn's rings will not exist in hundreds of millions of years' time. So those of you who like to see it through a telescope, make sure you see it soon because it won't be there forever. Still on the timescale of 100 million years or so, we have to remind ourselves that although we think of the solar system as a piece of clockwork, whether it be an orrery on the left or a tellurian on the right, we have to remind ourselves that the solar system is not clockwork. It's actually unpredictable. It's chaotic on timescales of order 100 million years. So we can work out where Jupiter is now and how fast Jupiter is moving, for instance, and we can calculate where Jupiter is going to be in 10 years' time or 1,000 years' time or many thousands of years' time. Or we can dial the clock backwards and work out where it was in the sky. For instance, was a Jupiter and Venus conjunction the Star of Bethlehem? We can ask ourselves those questions because it's easy to do the calculations over thousands of years. But we can't do it over timescales of order 10 to the 8 years because the solar system is chaotic. We don't even know how many planets there will be in the solar system on this timescale. It might be that Jupiter decides to throw out one of the smaller planets. Indeed, the early solar system was thought to be very different from the solar system we see today, and things have changed. Planets have changed positions. Some planets may have been thrown out of the solar system in the past, and they may do in the future. So although it's tempting to think of the solar system as basically clockwork, it quite definitely is not. Still on a timescale of 100 million years into the future, we live in the Milky Way. There's us at the moment. We are there, sitting in between two major spiral arms of the spiral galaxy. But on a timescale of 100 million years or so, that's roughly how long it takes the Milky Way to rotate. We are going to end up in a denser region. In 100 million years or so, we're going to move from a low density region in between two spiral arms into a higher density region within a spiral arm itself. What's the consequences of moving into a spiral arm? Well, it's twofold. We are going to have a lot more stellar neighbours. At the moment, we've got a certain number of stars within a few light years of our position. But if we're in a much denser region of the Milky Way, we're going to have a lot more neighbours. Remember what happened with Gliese 710. If stars get close to us, they can disturb the Oort cloud. And that probably means when we're in a high density region of the Milky Way, we'll have a lot more disruptions of the Oort cloud and a lot more asteroids and comets are going to be thrown in our direction. And perhaps that's going to lead to more extinction level events. If we look at how many species have become extinct as a function of time, this is present day on the right and the past on the left, we see that there have been spikes in the number of extinctions, and they've been how many? A few of them over a period of a few 100 million years. So it's not by clockwork by any means, but on timescales of order 100 million years, we can expect to have another extinction level event. The last one on the right hand side there, the KT one, that's the KT, meaning the boundary between the Cretaceous and the Tertiary. That's the impact of an asteroid that produced the extinction of the dinosaurs and of course many other species as well. So we're due for another extinction level event. Who knows what it's going to look like? There's an artist's impression of a big rock coming our way. If you look on the left-hand side, it looks like it's heading for Italy. Well, that's bad news for Italy, but of course, if it's large enough, it's going to be bad news for the entire planet, because species will be exterminated if a large enough rock hits the Earth. The real question is, will one of those species include us? And it's almost impossible to say. We've survived previous extinction level events. Let's hope we survive the next one. But there's a second consequence of having lots of neighbours. Not only are we going to have more asteroids coming our way, but having more neighbours means that we're more likely to have a star go supernova close to us. A supernova within 100 light years would definitely be dangerous for Earth. If a supernova occurred within 20 light years, it might conceivably produce enough radiation to end all life on Earth. Now, at the moment, we don't have any stars close to us that are supernova candidates. But in the future, when we're in a much denser region of the Milky Way within one of the spiral arms, we'll have many more neighbours. Perhaps one of those neighbours might be a candidate for supernova. We know it's happened in the past. If we look at the record, the sediment record of the Earth, we know that supernova within 100 light years have gone off in the past. And they've deposited a particular isotope called isotope 60 iron, or iron 60. This particular isotope is made during a supernova, but doesn't occur naturally. And it's radioactive. In other words, it only lasts some millions of years. A isotope iron 60 will change over millions of years into an isotope of something else, cobalt or nickel. That means if we find any iron 60 in the Earth's sediments, it can't be natural, it can't have been there since the birth of the Earth, because all of that would have decayed billions of years ago. So anything we do find in the sediments of the Earth must have arrived relatively recently. And therefore we know that there have been supernova go off in our vicinity in the historical past. And therefore it's likely that it will do again. There will be some neighbours becoming supernova, giving a threat to life on Earth in the future. In 10 to the 8 years, the distance to the moon will increase, because all of this time the moon has been applying the brakes to the Earth. The Earth has been slowing it down because of the drag of the drag of the moon. The moon raises tides on the Earth, and then the moon pulls on those tides, that body of water, and it slows the Earth down. So the rate of spin of the Earth has been decreasing, and the angular momentum has been transferred to the moon, so the moon is getting further away from the Earth, increasing its angular momentum. The Earth has slowed down to the point where the length of the day is now 25 hours. There's no point in thinking about how to add leap seconds to keep the clock synchronized with the Earth's rotation. We'll have to give up on that completely and perhaps decimalize our notion of how many hours there are in a day. But the distance to the Earth from the moon, or the distance of the moon from the Earth, will be so large at this point there'll be a couple of consequences. One will be that we'll no longer be able to see a total eclipse of the sun. The disk of the moon, because the moon is now further away, the disk of the moon will no longer be large enough in our skies to actually cover the disk of the sun. And therefore we'll never see a total eclipse. As indicated by the astronomy picture of the day on the right, the best we will hope for in this far future is that we'll get annular eclipses. The disk of the moon not being large enough to cover the sun, we would either get a partial or an annular eclipse where we would still see a ring of light around the rim of the moon. But although that's a bit of a shame, no more total eclipses. Again, for those eclipse chasers in the audience, get in now, because you've only got 1 billion years before there won't be any more. A more serious consequence is the fact that the moon has a stabilizing influence on the tilt of the Earth, the so-called obliquity. And from historical records, we think that the tilt of the Earth, currently about 23.5 degrees, in other words, the tilt relative to the perpendicular to the orbit of the Earth around the Sun, that tilt hasn't changed by more than about 1 degree either side of 23.5. The cartoon on the left shows you what that variation might have looked like. From about 22 to about 24 and a bit degrees, not much variation. So the seasons haven't changed that much for a long time. But if the moon moves further away from the Earth, then it'll no longer have that stabilizing influence on the Earth's axis, and then the Earth's axis might erratically change. It could change from 23 degrees to 0, or possibly even 90 degrees, and there would then be erratic changes to the Earth's seasons. There would be wild variations in climate if the Earth's axis isn't pinned at 23 degrees. So not having the moon as a close neighbour is a very serious problem. It could get very difficult for us. Still at 10 to the 9 years in the future, we can think about Voyager. Remember, that would have left the solar system and passed another star after 30 or 40,000 years or so. So after the time period of about 1 billion years, it will have had time to pass through tens of thousands or hundreds of thousands of different solar systems. After 10 to the 9 years, it's thought that the disk that Voyagers are both carrying will start to degrade. Why is it so much longer than Pioneer? Well, remember the Pioneer plaque, the Pioneer 10 and 11 plaque, was exposed to the interstellar medium and so got pitted after 10 million years or so. Voyager's gold disk is expected to last longer because the disk on the right is actually protected by a cover on the left. So the cover on the left is going to get pitted, but the disk itself will be protected as it passes through the interstellar medium. But there is a catch. The phonograph on the right contains various sounds and images from Earth, but unfortunately the cover on the left, which is going to get eroded, that contains the instructions for how to read the disk on the right. So if Voyager's disk or Voyager spacecraft is picked up after about 1 billion years or so, having passed through tens or hundreds of thousands of solar systems, if it hasn't been picked up by an alien civilization by then, anybody that does pick it up is going to find it problematic to read the disk simply because they'll no longer have the instructions telling them how. Still on a timescale of 1 billion years or so, the sun is slowly going to change as it very slowly starts to run out of fuel. The sun's luminosity is going to grow as it starts to move towards its red giant phase. Now, it's not a red giant yet at this point, 1 billion years into the future, but it's going to be increasing its luminosity maybe 10% every billion years. And that's going to drive the temperature of the Earth up. Perhaps the surface temperature of the Earth could reach 80 Celsius. So that's going to be a problem. The oceans are going to boil and we have to decide what we're going to do. Are we going to leave Earth until it's cooled down a bit, or are we going to do something else? The sun will expand into a red giant a few billion years into the future, and the surface of the red giant sun is going to get close to the Earth. And that indeed could be a problem. It's often been said that the sun is going to expand until it's a red giant that's so large it will engulf the Earth. Its radius will be larger than the radius of the Earth's orbit. Well, the latter statement is true, but it doesn't necessarily mean the Earth will be engulfed by the sun. Because as the sun expands, as it goes to its red giant phase, there will be very strong solar winds. In other words, a lot of mass will be lost from the surface of the sun. If the sun loses mass, then with less gravity pulling on the Earth, that means the Earth orbit will expand. So the cartoon on the left shows what might happen. As the sun expands, the Earth will move away from the sun, and so yes, the sun will eventually be large enough to engulf the original orbit of the Earth, but maybe the Earth won't be there anymore. The Earth might survive. It'll end up perhaps roughly where the orbit of Mars is currently. Different people disagree with this. You have to take a lot of different factors into account, but it's not necessarily obvious that the Earth will be engulfed by the sun. Let's assume for the time being the Earth survives. The outer part of the sun's atmosphere, once it's become a red giant, that will be sloughed off into a planetary nebula, and what's left behind, the core of the sun, is what we call a white dwarf. Essentially mainly carbon. It starts off quite hot, but it will simply cool down because there are no longer any nuclear reactions going on at the centre of the sun. Maybe it's just a lump of carbon, could conceivably be a lump of diamond. We don't actually know because we're not sure exactly what pressures exist within the centre of a white dwarf. But on this timescale of many billions of years, leading towards 10 billion years, not only does the Earth have the problem of surviving the red giant phase of the sun, it has to contend with the fact that it's going to lose its magnetic field. The core of the Earth is going to cool. The core of the Earth is not being kept warm by the sun. The core of the Earth is being kept in a liquid state by the heat generated by lots of radioactive elements in the core of the Earth. As these elements decay, they release energy, and that keeps the Earth's core molten. But eventually this radiation, this radioactive decay, will not be enough to keep the molten Earth core as a liquid. It will solidify. And once the core of the Earth solidifies, we lose the liquid dynamo that's generating our magnetic field. And hence, when we lose the magnetic field, we're then exposed to radiation, perhaps not so much from the sun, but certainly from the rest of the universe. Cosmic rays will rain down on the surface. It's thought that this is what's happened to Mars in the past. Mars is smaller, its core will have cooled before the Earth's core has cooled, so perhaps a long time ago Mars had a core which solidified, which means Mars lost its magnetic field, and perhaps that is what led to it losing its atmosphere. So the Earth, if it survives the sun going through a red giant, if it survives the loss of a magnetic field, then given that bad luck always comes in threes, you can ask what's going to happen next. And the answer is the Andromeda galaxy is going to come crashing into the Milky Way on this sort of timescale, a few billion years to 5 or 6 billion years into the future. We can calculate how much the Andromeda galaxy is moving towards us, and we think that on a timescale of about 4 to 5 billion years, the two galaxies are going to pass through each other. It's unlikely that any given star is going to collide with another star. It's more likely that all the gas and all the dust will interact, and there'll be lots of tidal forces between the two galaxies, but it's unlikely that a particular star is going to be impacted. So the sun will probably survive. But as the two galaxies pass through each other, there's going to be a riot of new star formation. And the galaxies will pass through each other, and temporarily there will still be two galaxies, but then gradually they will merge together over a period of a few billion years. And here the state after 5 billion years seems to show a galaxy where there's no sign of the spiral arms that we're used to in the Andromeda and in the Milky Way galaxies, and it looks like we have two bright nuclei. These will be the nuclei of what used to be the Milky Way and the Andromeda galaxy. Those are where the supermassive black holes exist, and eventually those two supermassive black holes at the centre of those two galaxies will merge into one big supermassive black hole. And the galaxy that results, I don't know what we call it. Do we call it Milky Way? Do we call it Andromeda? Do we call it Andrilke? Do we call it Milkdromeda? I don't know what its name will be, but eventually it'll settle down as a large elliptical galaxy. We'll lose the spiral arms that we like to see in spiral galaxies. On a scale of 10 to the 11 years, the moon has finally taken all the angular momentum it can out of the Earth. At this point, one day is the same as 1 month. In other words, the length of time it takes the Earth to rotate once on its axis is the same as the length of time it takes the moon to do one orbit of the Earth. So the Earth is now tidally locked to the moon. One side of the Earth will always face the moon, just like at the moment, one face of the moon always points towards the Earth. So if you were in one particular continent on the Earth, the moon will be unchanging and fixed in the sky. It will never rise and never set. Whereas if you're in the opposite side of the Earth, the moon will never be visible. It will never rise above your horizon. This is pretty much the same as what Pluto and Charon are now doing. They are two bodies that are so close together, they always have the same face facing each other. Eventually, that's what will happen to the Earth and the Moon. And if that's picture there looks like a Photoshop, no, that's not a Photoshop picture. That's a genuine picture of the Moon and the Earth. Of course, we're looking at it from beyond the Moon, and hence we're looking at the far side of the Moon rather than the more familiar near side of the Moon. We're now looking at a timescale of 10 to the 12 years into the future. What's going to happen to the galaxies in our local group, our immediate neighbourhood? The Milky Way is surrounded by lots of small galaxies, dozens if not 100 or so small dwarf galaxies like the Magellanic Clouds, for instance. And we know that the Milky Way is going to hoover all of those up. Basically, galaxies are cannibals, and the large galaxies will eventually eat up all the smaller galaxies. So we know the Milky Way is going to collide with the Andromeda Galaxy M31, eventually M33 will join us, and all of the other small galaxies in the entire local group will merge into one mega galaxy. It won't be a spiral galaxy, it more likely be an elliptical galaxy. What's going to happen to galaxies beyond the local group? Well, we know that it's possible now to actually image galaxies that are receding from us at greater than the speed of light. That's one thing I did as a lockdown project back in 2020 with my camera without using a telescope. I imaged the nucleus of a galaxy called a quasar, which is receding from us at something like twice the speed of light. And if we have a look at the Hubble Deep Field, in this case the Ultra Deep Field on the right hand side, most of the galaxies that we can see, certainly the distant ones in that particular image, most of those distant galaxies are receding from us at greater than the speed of light because of the expansion of the universe. Some of the very close galaxies might be receding from us a little slower than that. But 10 to the 12 years into the future, the expansion of the universe will continue, and it won't be too long before galaxies are so far apart from each other as the universe continues to expand for another trillion years. If it continues to expand, the galaxies will be so far apart from each other, it'll be impossible to see them. And so an ultra-deep field of the Hubble Space Telescope would show us nothing except the two stars that happen to be in the field of view that belong to our Milky Way. And it's sobering to realise that if any civilization comes along in a trillion years or so, if they build themselves the equivalent of a Hubble Space Telescope because they're interested to see what does the universe look like, if they point their telescope into deep space and take a long exposure, they will see nothing. They will only see the stars in their own galaxy. So they will come to the conclusion that the entire universe comprises just their own galaxy, because they will not be able to see, for instance, the trillion galaxies or so that we can see when we look out into the universe. A sobering reminder that we live in very interesting times compared to the distant future. I said in the beginning of everything that it took, roughly speaking, 3 minutes to make all of the protons, all of the neutrons that give us the hydrogen and helium in the universe. So if it took 3 minutes to make all the hydrogen, well, after a trillion years, it's starting to run out. It's almost all gone. And if there's no more hydrogen, how are we going to make any new stars? Well, when we think about how stars evolve, we think we need hydrogen to make stars. But some people have hypothesized, well, maybe it's possible that stars might form from heavier gas, heavier elements. Not everybody agrees that's possible, but some people have hypothesized, instead of starting with hydrogen, is it possible to start with heavier elements? And people have done calculations that indicate it might be possible to have a star with nuclear reactions occurring at the core, fusion reactions at the core, but a surface temperature that's substantially lower than, for instance, the surface temperature at the surface of a red giant, which is about 3000 Kelvin or so. Maybe the temperatures could be 10 times less than that. Maybe instead of thousands of Kelvin, the surface temperature could be perhaps hundreds of Kelvin. Is there any reason why you can't have a star with a surface temperature of 0 Celsius? Frozen stars. Okay, that's the Disney version of a frozen star. That's not what I'm talking about. If that's the picture in your head, then let it go. Because what I'm talking about here is a star in which fusion reactions are occurring at the core, but ice in principle could exist in the atmosphere, in the outer layers of the star. That's a little bit of a hypothesis. But before we go any further, so as to make sure that we understand what the universe is doing, let's just very briefly remind ourselves of how the universe is expanding. So this is the size of the universe on the vertical scale as a function of time across the horizontal axis. That's where we are now. Let's just say that the universe has a size of 1. It doesn't matter what distance we're talking about. Let's just call it a size of 1. We can see that because the universe is expanding, we deduce it was smaller in the past. But how long ago do we go back to the Big Bang? Well, that depends on these 4 colours. It's the model of the universe that we choose, and the model depends on how much matter there is out there, how much mass, how much energy is there in the universe. That determines which of these 4 coloured lines actually tells us how the universe is expanding. So, for instance, if the universe contained a huge amount of matter, the orange curve, then you can see that what's going to happen in the future beyond now, it gets larger and larger and larger, but after a certain point it starts to get smaller and smaller until we end up with a situation called the Big Crunch. In other words, if there's enough mass in the universe, gravity is going to get a hold of that. There's enough gravity to stop the expansion and to reverse the expansion and to bring everything back again, a so-called closed universe. But we don't think that's the universe we live in. When we look and try and find out how much matter is there out there, we come to the conclusion that, well, it looks like we're on the red line. We think the amount of matter and energy in the universe is such that what's going to happen is we follow the red line in the future, which means the expansion is not only going to simply continue, but notice that the gradient is getting larger and larger. This line is flexing upwards. Some time ago we thought maybe we were on the green line in that it's continuing to expand but it's flattening off, but now we think it's continuing to expand and the rate of expansion is increasing. The expansion is accelerating. So we might be wrong on that, but at the moment it looks like we're on the red line, which means the universe is going to expand forever. And in order for this talk not to take the next 3 or 4 hours, we're going to change gear. So now we're going to have a timeline of boxes along the top where each box is 1,000,000 times further into the future than the previous one. So we're now talking about a zillion years into the future, or I don't know what names we're going to give these things. We're just going to have to rely on the numbers to talk about 10 to the power big numbers into the future. So where did we leave the universe before we took this little aside to remind ourselves that the universe is expanding and accelerating and looks like will expand forever? Well, we said at the end of the last section, it looks like, although it took 3 minutes to make all the hydrogen, after 1 trillion years or so, it's starting to run out. Now, if we can't make new stars out of fresh hydrogen, because we haven't got any fresh hydrogen, stars might live for an awful long time. They can live for trillions of years, but they don't live forever. So what does that mean? the age of starlight will come to an end. There will be a time when there are no more stars burning any fuel in order to make starlight. The dead stars will continue to orbit their galaxies. They'll be drifting through space like zombies, white dwarfs, neutron stars, black holes, stars that have come to the end of their life so that nuclear reactions are no longer occurring in the centers of these objects. White dwarfs, okay, they're white to start with because they're hot, but they will simply cool off. With no nuclear reactions to keep them hot, a white dwarf will end up as a black dwarf. Just a lump of carbon, possibly a diamond, but basically a lump of mainly carbon. That picture on the right, you can probably hardly make it out. If I make it a bit brighter, that doesn't help much. It's a large black object. Some stars will simply be ejected from the galaxy, and some will be eaten by the central supermassive black hole that we believe is at the center of essentially every galaxy. Magnetic fields have been mapped out in another galaxy called NGC 1097 using an infrared telescope in Sophia. Sophia is the 747, which is the stratospheric observatory for infrared astronomy. In the back end of the 747 there's an infrared telescope, and the 747 used to fly above most of the atmosphere to avoid most of the infrared getting absorbed. Sadly, Sophia has now been decommissioned, but one of its more recent observations was to map out the magnetic field lines that we can see here on the left-hand side, and it's thought that matter is funneled through these magnetic field lines, or at least follows the magnetic field lines, and ending up in the supermassive black hole right at the center. We can't image the supermassive black hole directly, but it's in this central region here. And so we think that all matter that's not actually thrown out of the galaxy will end up being pulled into the supermassive black hole. What happens to all the atoms in the universe? Well, the notional picture of an atom is positive charge in the nucleus and lots of negative electrons buzzing around outside. Protons are the particles that are responsible for the positive charge in the nucleus of every atom. But it is possible that protons decay. They change, they disappear, in which case atoms will fall apart. We don't know the timescale over which this is going to happen. We don't even know if it does happen. If it does happen, it won't be any sooner than about 10 to the 36 years or so. So atoms ultimately will not exist beyond this point. But if we assume that proton decay doesn't happen just for the time being, and atoms exist for a little bit longer, well, they don't exist forever. Because even if protons don't decay, then the black dwarfs, which are effectively the only source of protons now, neutron stars don't contain protons, they only contain neutrons. Who knows what's going on inside black holes, but it's probably not individual protons and neutrons. So the only source of atoms is basically black dwarfs, and they eventually evaporate to leave no atoms at all in the universe. Black holes will merge together. We know that black holes at the center of galaxies, when galaxies collide with each other, which they do all the time because that's a natural process, it's part of galaxy evolution for galaxies to come together and merge, then the black holes at the center of those galaxies will merge together. And so instead of having black holes which might be millions of solar masses, such as the one in the center of the Milky Way, not necessarily billions of solar masses, but when enough black holes merge together, it is possible that we end up with absolute monsters with masses of trillions of solar masses. But black holes do not last forever. They are not eternal. Even black holes will evaporate, providing that you wait for a really long time. So let's just briefly think about why black holes evaporate. Well, there's a certain rule in quantum mechanics that says, well, you can borrow stuff from nothing. You can borrow energy from nothing, and you can make matter and antimatter. You can make particles and antiparticles by borrowing energy from nothing, as long as those particles and antiparticles annihilate and pay back the loan on short timescales. In other words, we get energy, we get particles, we get the energy back again. Let's just see that again. We borrow energy, we make matter and antimatter, they annihilate, and we pay back the loan of the energy we just borrowed. How does that help us understand the lifetime of black holes? Well, Stephen Hawking asked the question, what if this process, which we think is going on all the time, what if it happens just outside the event horizon of a black hole? What if we borrow some energy, make matter and antimatter, and one of them has fallen into the black hole and the other one hasn't? So now they can't annihilate. So it looks like something has come out of the black hole. Strictly, it's come from just outside the event horizon, but there seems to be a flux of something radiating from a black hole. We now call this Hawking radiation. And according to Hawking's calculations, the radiation increases with decreasing mass. As the black hole gets smaller and smaller, the radiation gets stronger and stronger. So small black holes evaporate faster than large ones. So as a black hole evaporates, the radiation levels increase, the black hole shrinks, which means the radiation gets even stronger, until finally, as a sort of avalanche effect, it finally disappears in a flash of radiation. Even the really big ones, even the supermassive black holes, which might have trillions of solar masses, even they will evaporate eventually, as long as you wait trillions of times longer than the length of time it takes for a solar mass black hole to evaporate. So have we reached eternity? Well, strictly speaking, no. But let's take an arbitrary point of 10 to the power 100, a so-called Google. No, not that Google, that's just a misspelling of the actual Google, 10 to the power 100. After a Google years, the last black hole will have evaporated. And then there will be no matter left in the universe. There will just be radiation. There will just be lots of electromagnetic waves getting stretched further and further and further and further as the universe continues to expand. Once all the matter has gone, nothing happens. Nothing interesting happens from that point onwards except that the universe continues to expand. And so time becomes essentially meaningless. 10 to the power 100 is a ridiculously long length of time. I don't normally put the zeros in, but just to remind ourselves how big 10 to the power 100 is, let's just write it out in full. There it is. 10,000 million, 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 etc., etc., etc. It's too large a number for us mere humans to get our heads around, but it can be calculated that that's the timescale on which the universe doesn't come to a halt, but nothing interesting happens after this point. As Woody Allen said, eternity is a very long time, especially towards the end. Another way of putting human perspective on these very long time periods is to remind yourself, according to XKCD cartoons, a human is a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking email a lot. That's an interesting way of thinking about humans on these ridiculous timescales. But in order not to leave on too depressing a note, let me finish with an epilogue. We live in a golden age. The sun is middle-aged and well-behaved. The moon is at the right distance to stabilise the Earth's axis and hence stabilise the Earth's seasons. And thanks to evolution, we're able to explore and discover and understand the universe in which we live. We can build ourselves space probes and we can go and visit our closest neighbours. Or we can build ourselves telescopes in which we can see trillions of galaxies at distances of billions of light years. Now, humankind could not have existed in the very early universe. We needed a consecutive series of generations of stars needed to make the heavier elements. We needed stars to convert hydrogen into helium, and then helium into carbon and nitrogen and oxygen and calcium and phosphorus and iron. All the elements that we need to make us us. And we've seen that trillions of years from now, the universe will be dark and the universe will be boring. So you could say the best time to exist is now. Thank you for listening.